Hello, welcome back to the part two of this lecture on mixture distribution and Bayesian statistics. Uh, and then in this part, we will go into a new topic also. But let me just briefly recall what we discussed in part one. We started with the definition of mixture distributions. And I explained the meaning of a mixture distribution and how a mixture distribution can have several modes or still a single mode, depending on how separated the individual distributions are. That is one thing that we discussed. Uh, in this lecture, actually, we are considering only two components of the mixture because it is easier when you have only two components, two groups. But in general, we can expand that idea to several groups also. So you can have generally a mixture of several distributions in general. Right. We looked at several examples. First example we looked at was the joint mixture distribution of the heights of men and women. Right. So in that case, we knew the distributions of heights in each group separately, and also we knew the proportion of each group from the population. So based on that, we can derive the mixture distribution. And once we know the mixture distribution, Bayes the theorem, using the Bayes theorem, actually what is important is uh, we can predict the gender of a person when we know uh, the height. So in this example, we looked at that kind of problems. Here we had the densities of heights for men and women, and we knew the proportion of each group. And using that, the mixture distribution actually looked like a unimodal distribution in this particular case. And then for example, predicted once we know the height of a unidentified person, whether we don't know whether that person is a male or female, only the height is identified. Uh, so we wanted to predict whether the person is a male or a female. So that kind of predictions can be applied, done uh, using this idea, right? When you know the mixture distribution and individual distributions, right? So then we discuss about the threshold, classification threshold based on some Bayesian idea, right? So we decided below or above which height a person would be decided to be a man or woman. So that height where the height distribution will be divided into is called the classification threshold, and that we discuss that kind of examples. And then we looked at another example where we wanted to predict whether a certain application for mortgage would be a default applicant or non-default, right? So that is also a practical example. We looked at that example, right? So based on about 1,000 mortgage applications and past experience, we knew some information, right? Uh, how many of those applicants were defaulters and how many were non-defaulters, and also we had information about their income distributions for the two groups. So based on that, uh, what is interesting is to classify a new application as whether it will be it will be a default or not. So that example was discussed in the part one. And then we looked at another example where we tried to decide out of two teams which team was better based on very restricted small number of observations. For each team, we had only a few number of observations from previous games. So based on that, how to decide. We discussed how to answer two questions. One first question is which team is better. So there we had to define what we mean by better, right? So we discussed several criteria for that. And then second question was which team had a higher probability of winning a future game. So that was a different question. So those two questions were discussed under different approaches. So you can look at how we tackled that problem if you watch video one, like part one of this lecture. So to continue, uh, before we come into the next topic, I will look at one more example here, very similar to the previous one. Here we are going to look at two fighters. Uh, we know some information about their previous fights. Fighter A has won 13 out of 13 games, 13 fights, and the fighter B has won 26 fights out of 31 fights. Right. So here also the question is there are two questions. Which fight is better is one question, and which fighter has a higher probability of winning in a future game, future fight? That is the second question. Right. So let's look at the same procedure as the previous example. We will follow the same procedure. Uh, so let PA and PB denote the underlying winning probabilities of fighters A and B. Right. So these are usually considered as constants, unknown constants. But in this approach, we are going to consider them as random variables, right? Underlying winning probabilities of A and B, right, respectively. Here we are considering their winning probabilities when they are fighting some other fighters, not against each other. Right. So we don't have much information, but in this kind of situations, it's common to select uh, a distribution for PA and PB using the conjugate idea. Right. We have discussed this idea very briefly in a previous video. What do you mean by a conjugate distribution? So in that discussion, actually, we showed that when the likelihood function of the data uh, is binomial, usually we select beta distribution as the conjugate prior distribution for the uh, probability of a success. So following the same idea, here we are going to use the models, prior models for PA and PB. We are going to assume both are uniform, IID uniform uh, in 0, 1 interval. So that means PA is uniformly distributed in the interval 0, 1. PB is also uniformly distributed in the interval 0, 1, and they are independent. Actually, uniform 0, 1 distribution is a particular or special case of a beta distribution, beta family. So uniform 0, 1 is actually the same as beta 1, 1 distribution. So therefore, equivalently, we can say that we are assuming PA and PB as independent beta 1, 1 random variables. So therefore, the data that we have, XA and XB, XA and XB denote the number of previous fights won by the two fighters, right? So conditional on their winning probabilities now, we assume that actually we can reasonably assume this thing as binomial because it's out of a fixed number of fights, assuming that each fight has a equal probability of winning. So that is a kind of a strict assumption. But under that assumption, and also assuming that winning or losing in one match doesn't depend on VC, winning or losing in another match. That is also kind of a little bit strict assumption. But under those strict assumptions, we can assume that XA given PA is equal to some value PA will be binomial uh, with n equal to 13 and probability of success with this given PA value. And similarly, XB will be binomial when PB is given as PB, binomial with n equal to 31 and P probability of success being equal to PB. Right. So the observed results are XA is equal to actually 13 and XB is equal to 26. So therefore, we can write down the likelihood functions of PA and PB given the data. They are the same as actually the probability that X equal to 13 given PA is equal to PA. Right. Now here we are interpreting this probability as a function of PA. Then we call it the likelihood function. Right. So that is the probability of observing what we have observed already. Right. We have we have observed already something. So what we are looking at is if the probability is PA, what is the probability of observing something similar to that, right? So that when you look at as a function of PA, it's called the likelihood function. So it is given by this expression, it comes to PA to the power of 13. And if you multiply that uh, by the prior distribution that we assume, then we can show that the posterior distribution of PA given XA is equal to 13 has a beta 14 1 distribution. We did a similar derivation in the previous example in part 1. So I encourage you to go and look at that derivation. I have given you some general result also. So if you multiply this likelihood function by the prior distribution, which is again a beta distribution, this binomial, then the posterior becomes again a beta distribution. And similarly for pi to b, the likelihood is given by this, that is the probability that xb is equal to 26 given pb is equal to pb when considered as a function of pb. It's called the likelihood function of PB. It has this form. And then when you multiply that by the prior distribution of PB, which is again beta distribution, then the posterior distribution of PB becomes again a beta distribution. It becomes beta 27, 6. So I have not shown the complete derivation here, but because I have shown the complete derivation in the previous example, uh, I have only shown the final result here for the posteriors. So now once we know the posterior distributions, we can start answering the two questions that we wanted. We will answer the first question. What is the probability that which fighter has a higher probability of winning a future match, future fight? So for that, what we do is we calculate the posterior predictive probabilities for each fighter. Posterior predictive probability. Right. We know the posterior distribution of PA. We know the posterior distribution of PB. So posterior predictive probability is actually the posterior mean of PA and posterior mean of PB, right? So that can be interpreted as the probability that fighter A wins a future fight, given the observations that we have, right? So here we are finding the probability that the fighter A wins a future fight, and that is given by the expected value of the posterior distribution. Expected value of PA given XA. So this is the posterior expectation. Now, because the posterior distribution is a beta distribution, using the knowledge that we have about beta distributions, we can directly get the mean of the beta distribution. Right? So it's going to be alpha divided by alpha plus beta. So therefore, uh, posterior expected value for phi A is 0.933. Right? And then the same probability for the posterior expected value for phi B is 0.818. Right? So using the same method. So using these two then, because this number is larger than this one, so phi A has a larger posterior predictive probability of winning a future fight. So that is how usually the Bayesians decide what is the which person has a higher posterior probability of winning, right? Future probability of winning. So that is the answer to one part. And to answer the other part, which fight is better in general, right? Usually we look at the probability that one probability is greater than the other probability. Remember, these probabilities are now random variables. So therefore, it's meaningful to talk about what is the probability that, for example, PA is greater than PB. Right? If this probability is greater than 0.5, then you decide that fighter A is better than fighter B in general. So that is the method. So we are going to look at the posterior probability of PA being greater than PB. If you want, you can look at the other way around, probability PB greater than PA also. But here I'm looking at this probability. So if the better fight is defined as the fighter having the large underlying winning probability, we would calculate this probability. Right. So in order to calculate that probability, we need the joint probability density function of PA and PB posterior, right? So that is given by actually because individual posterior distributions we know them. We know that PA and PB are independent. Therefore, the joint posterior probability density function is equal to the product of the individual posterior distributions of PA and PB. So when we substitute the individual beta distributions that we had, we get this expression. We can simplify it as this expression here. Right? This one is a beta distribution. This is also a beta distribution. So when we put down, we get this expression here. Now we want to integrate this joint density over a subset of the support satisfying this condition. Right? The support here is actually a square, right? PA can be between 0 and 1. PB can be 0 and 1, between 0 and 1. Generally, they are independent. Therefore, the support will be a square, right? Where one side has a length 1. Right. But what we are looking at is actually the volume spanned by the joint density function over a subset of that support. So that subset satisfies this condition. So therefore, we can easily understand that. So these are the general restrictions for PA and PB independently. So therefore, the domain, not actually the support will be the square. But now we are looking at the volume under this region here, set of PA, PB values, so that PB is less than PA, and both are between 0 and 1. Right. So it's a subset of the unit square. So in order to get that volume under the joint density function over that region R, we have to integrate the joint density function with respect to PA and PB. When you are integrating here, I am integrating here with respect to PB first. So in that case, the limit will be going from 0 to PA because PB is between 0 and PA. And then when you integrate with respect to PA, it has to change from 0 to 1. Right? So here, mm, or you can write down the same thing. If you change this to integrations, you can write down it like that, right? So in any way, here I am considering now, in this case, actually, if you look at the joint density, you can easily see that this thing can be factored into two products. This part will be, this is only a function of PA, and this thing is only a function of PB. And therefore, we can easily separate those things when you are integrating, right? Integrate this thing with respect to PA first, and then put the limit from PB to 1. And then everything will be in PB. Then you can integrate with respect to PB, right? So when you are integrating this with respect to PA and put the limit from PB to 1, you get this part, and then whole thing is coming like this to integrate with dp pb, and then you can see that this is equal to this thing times 1 minus this thing times this part. So therefore you can say partition, actually write down it as sum of two integrations, right? So like this. So each, this one is a beta distribution here without the uh, this has the form of a beta distribution without the normalizing constant. So therefore, the answer for this thing when you are integrating from 0 to 1 should be the normalizing constant. So that will be beta 27.6 coming from this one. When you do this integration, that will be again this beta term that is equal to the normalizing constant, 1 over the normalizing constant. So this thing is there. When you simplify these all these things, even you don't have to come to this part, you can just simplify this. Okay, you can cancel out. So you get into 0.903 here. So that is the probability that PA greater than PB when you know that XA has been 13 and XB has been 26. Right. So therefore, under the uniform prior model, that those are the models that we used, there is approximately 90.3% posterior probability. Actually, it's not really correct to talk about probability as a percentage. It's better to say 0.903 posterior probability. That fighter A has the larger underlying meaning probability. Therefore, the available results favor fighter A. So that means we say in general, fighter A is better than fighter B. But of course, you have to remember at the beginning, I mentioned the data that we had was not they didn't come from fights among them. They came from fights with some other fighters. So therefore, this value 0.903 is a posterior, excuse me, is just a posterior probability that PA greater than PB. Thus, under the uniform prior model, there is approximately 90.3% posterior probability that fight A has a larger underlying meaning probability. Right. So I have to mention that these words came from an AI actually. This is how AI is interpreting it. But I would like to mention that usually when you talk about probability, it is better to avoid percentage because we know that the probability is always a number between 0 and 1, whereas the percentage is a number between 0 and 100. So it's not good, even though it's kind of intuitive and we understand what we mean by that. Especially technically, when we talk about probability, it is not good to mention probability in terms of percentage. So even though it's mentioned here by, because I have got help from AI to produce this, uh, some of the interpretations here, but it's better to mention it as 0.903. So fighter A has the larger underlying meaning probability. Therefore, the available result favor fighter A. The same thing that I mentioned here. However, this is the important part. However, it is not necessarily the probability that fighter A defeats fighter B in a direct fight. It is not the probability that fighter A can defeat fighter B in this case, right? Because the data were not coming from those fights. So a direct head-to-head winning probability would require an additional model connecting the two fighters' abilities to the outcome of the fight between them. So that has to be understood. So here we are talking about in general what will happen and how which person is better in terms of when they are fighting with other fighters, not not when they are fighting each other. So that is an import, right? Uh, so that ends the discussion of that part. That is the mixture distribution and uh, posterior distributions, posterior predictive probability, and so on. That ends one part. And then now I come to the second part of this lecture. Uh, Here we talk about uh, a new topic called random sum and some examples where we are looking at random sum, right? So what does this mean, random sum? We have already looked at in a lot of situations where the quantity of interest is the sum of a fixed number of random variables. The number of terms appearing in the sum is a fixed value, like simple n usually we use. I from 1 to simple n, sum of xi's. Right? But there are situations where we are adding several random variables. The number of random variables we are adding is also random. Right? So sometimes we want to find the expectation of that kind of sums, also the distribution of that kind of sums, or the variance of that kind of sums, right? So that is the topic of this section. Sometimes we want to find the expectation of and similarly variance of sum of random variables with a random number of terms I from 1 to capital N xi, where capital N and x1 up to x capital N are random. To simplify, we shall assume that xi are iid conditional on n with distribution independent of n. So here in this discussion, we are going to assume that these xi's, x1, x2, x3 up to x capital N, they all are independent and identically distributed, which is not necessary in a general problem, but for simplification, we will start with that situation. X1 up to x capital N are IID conditional on N. Right. So N conditional on means when you consider given a value for N. And also their distributions are independent of the distribution of N. So that is another assumption, right? So how many terms going to be in the sum is independent of the distributions of X terms. Then we can use the rule of repeated expectation that we discussed in the previous lecture, actually, not part one, but in the previous lecture. Repeated expectation can be used to find the expected value of the random sum. Right? So, yeah, therefore, using something that we have already discussed. Right? So, what is interest what we are interested in the expected value of I from 1 to capital N summation of xi. So, but we know that if you consider some random variable like this, uh, it is equal to expected value of that random variable given another random variable. Here, the random variable interested in is sum of xi, but there is another random variable n. So therefore, it is meaningful to talk about the expected value of this quantity as the expected value of uh, the summation for a given n first, and then look at that, look at the expected value of that quantity. This quantity will be a now function of capital N. So the expected value of that quantity, considering n as a random variable. Right? So it is just a direct application of the repeated expectation formula. Okay, so for a given n is fixed. So therefore, we can consider now this as a fixed quantity. So in that case, the expected value of sum of x1, x2, x3 up to n, where n is fixed, is equal to sum of the expected values uh, of n terms. And because we are assuming they are IID, each has the same expected value. So you can call it expected value of x if you want. But here I have mentioned it as expected value of x1. It will be the same as expected value of x2. So this term will give you therefore n times expected value of x1. Right? The same term has to be added n times here. And then you have to now, this expected value of x1 is a constant. Right? But now n here is random when you are considering this expected value. So therefore, expected value of this quantity with respect to n can be obtained as by taking this thing out of the expected value first, because that is a constant, and then expected value of n. So that is where you get expected value of n times expected value of x1. So that is a very kind of an intuitive result also, right? Uh, Generally, somebody might expect this expression without any theory like this also, right? So it's expected value of the sum of capital N xi terms, x1, x2, x3, and so on, is equal to expected value of n times expected value of any xi term in this case, right? So that is one important result. So let's look at the variance also. Variance of sum of I from 1 to capital N. Again, you can derive an expression using the variance decomposition formula that we discussed in a previous lecture. Right. So that gives you the expected value of uh, this quantity for a given n, variance of the sum of x given n, plus the variance of the expected value of sum of x given n. Right. So this is directly coming from the previous lecture. Now, if we look at this quantity, we are looking at where n is, for a given n is now fixed. Here, this n is considered as a fixed value. Right. So here we have variance of sum of xi terms for a fixed n terms. We know that xi's are independent, and therefore, and also identically distributed. So therefore, what we will have from here is n times variance of xi for any xi. We will take it as x1, right? So from this part, it comes n capital N times variance of x1. And from this one, we get again here for a given n, uh, right? So this n is now considered as fixed. So therefore, expected value was sum of fixed number of xi terms where xi's are IID. So that will give you n times expected value of x1, for example. Right? So that's how these two terms come, expected value of n, and then n times variance of x1 coming from this one, and then the variance of n, right? Variance of n, and then from this one, n times expected value of x1. Now notice here, variance of x1 is a constant. So you can take it out of the expected value, and then you will have variance of x1 times the expected value of n, that is this quantity. And similarly here, expected value of x1 is a constant, but you are considering a variance, variance of some random variable times a constant. In that case, you know, when you take that expression is equal to the square term of the constant times the variance of n. So that's why you have here expected value of x1 square times the variance of n. So therefore, we get this expression for the variance of sum of uh, a random number of uh, random variables. Okay, so those are two important results. So let's now look at one or two examples. I will look at two examples. The first one is coming from the book again, Emilian example 3.40 regarding car accident claims. An auto insurance company wants to know the expected total amount of claims per month. It is known that the average number of claims is 1,128. So if you decide the number of claims as n, expected value of n is equal to this number. And the average claim is $3,500. What is the expected total amount? So this a direct application of what we just considered. So suppose S is the total of a random number of claims, where Xi is the claim of the ith, the amount of the ith claim, and n is the number of claims received during a particular month. So n can be a random number, Xi is a random number. So we are interested in the total, right? A summation I from 1 to capital and Xi, right? We are given that expected value of n is equal to this number, and expected value of the claim is equal to 3,500. So using the formula, we can directly get expected value of the sum of the claims per month is this number here in dollars. So that's a very straightforward example. Right. Similarly, if the question asks the variance, in that case, we have to know the variance of n and variance of xi also. If you knew those things, then you could have derived an expression for the variance of s also. But those information were not available in the problem, and that was not asked in the question also. Right. Now let us look at a little bit more practical type example. Uh, Derive the mean of the random sum with n following the non-zero Poisson distribution. Sorry, I had to pause recording for a few minutes because I got a call. So let me continue. So I was talking about this new problem where we are going to assume that n has a certain Poisson distribution. Of course, in a Poisson distribution, generally the value can be zero. But for this problem, n equal to zero is not going to be meaningful. So therefore, what we are assuming is that n has something called a truncated Poisson distribution, where n equal to zero is not possible. Right? So that kind of Poisson distribution uh, is available, and we can consider that Poisson distribution, truncated Poisson distribution, with zero truncated, right, as the distribution of n. Uh, And then for xi's, we are going to assume normal distributions, right? Each xi has a normal distribution. Derive the marginal variance using the variance decomposition formula. Derive the distribution of the random sum. And question is asking now xi's are random. So whether the sum of random numbers is also random, that is the question. Write R code to check the formulas via simulations and check the distribution by plotting the theoretical empirical CDFs on the same graph. Right. So it has several questions, several parts. So let's try to answer one by one. So we are considering a sum of n random variables where n has a truncated Poisson distribution, and each xi is assumed to have the same normal distribution and independent. So xi, x1 up to xn all are independent and identically distributed with mean, mu, and variance sigma square. Right. Suppose that n has a non-zero or zero truncated Poisson distribution with parameter lambda. Right? So in that case, the Poisson truncated Poisson distribution, truncated at zero, is given by this formula. So this is the mass function of that. What we want to look at is probability n is equal to simple n. That will be equal to the probability that value y is equal to n coming from a usual Poisson distribution divided by the probability that y greater than 0. Because if probability y equal to 0 is also included, then the sum of all the probabilities will add up to 1, and therefore uh, the mass function will be a proper mass function. But in order to consider zero truncated Poisson distribution, we will have to consider only possibilities 1, 2, 3 up to infinity. So therefore, uh, the probability n is equal to simple n is not directly equal to this part only, probability y equal to n, where y has a Poisson distribution with lambda. You have to normalize it by dividing by the probability where y is greater than 0. Right. So then this whole thing will give you a real probability mass function. Right. So therefore, it's going to be the probability y equal to n is coming from my usual Poisson, but probability y greater than 0 is going to be 1 minus the probability y equal to 0. So therefore, this is the actually the mass function of the uh, truncated Poisson distribution, where truncation occurs at 0. Right? So therefore, this is the probability mass function. That is the probability n is equal to n for the truncated Poisson distribution, where n doesn't include 0 now. N can be from 1, 2, 3, and so on only. But here y is the usual Poisson, where y can be 0, 1, 2, 3 up to 6. So anyway, this is the truncated Poisson distribution, mass function of the truncated Poisson distribution. Truncation is occurring at 0. Therefore, we can also get an expression for the expected value of n, because we need that one to get the variance of sum of x. So expected value will be just n summation n from 1 to infinity n times the mass function, right? So, but now because summation is going over n, you can take the parts which doesn't contain n out. So therefore, this term. Now, if you consider, if you take one lambda out here, you get this expression, right? And now you can actually see that this has some well-known form of an expression. In order to see that, let us change the variable of summation here. Let's take j is equal to n minus 1, right? So therefore, the summation will go from 0 to infinity. You will have here lambda to the power j and factorial j. So now you will understand, you will identify this term here, the summation term. This term here now is actually equal to e to the power lambda, right? You get this expression if you expand e to the power lambda using Taylor expansion around 0, right? So now, therefore, the expected value of n, where n has a zero truncated Poisson distribution, it is equal to this expression here, right? So this is very easy to see with that, because it is the same as the expected value of usual Poisson distribution with parameter lambda divided by that normalizing constant. We saw that earlier, normalizing constant for this one. This is the mean of a usual Poisson lambda distribution, right? So without this whole calculation also, we could have get this expression directly by arguing like that. Expected value of n should be equal to the expected value of the usual Poisson divided by the normalizing constant. Right. So anyway, I have shown you how to get that also using uh, the usual following the usual definition of the expected value. So in order to get the variance of n, we need expected value of n square. So instead of deriving the expected value of n square directly, it's easier to derive the expected value of n times n minus 1, because then some of the terms cancel easily, and then we can get a similar previous expression similar to that previous calculation easily. So that's why we, instead of directly getting expected value by n square, we are considering this thing. From this one, of course, we can, once we get an expression for that, we can get an expression for expected value by n square. That is the second step. Right. So therefore, this is equal to this expression, n times n minus 1 times the mass function of the truncated Poisson. Remember, notice here n goes from 0 to infinity. And then when this n to n minus 1 cancels out some terms with the factorial n, you are remaining with this one, right? So now if you take lambda square out of this, you will get this expression, right? And then if you consider n minus 2 as a new variable of summation j, you get this expression. And this is the same as e to the power lambda. So therefore, you get this expression for the expected value of n times n minus 1. So therefore, the variance of n we can write down as expected value of this quantity plus expected value of n minus expected value of n square, because you can see that what you need is the variance of n is equal to expected value of n square minus expected value of n whole thing square. Right? But here you get expected value of n square minus expected value of n, and you have to remove that by adding expected value of n. Right? So therefore, you get expected value of n square minus expected value of n whole thing square. That is the variance. So when you substitute the terms that you found, then you get this expression here. Right. So therefore, the expected value of S will be equal to expected value of X times expected value of N. Expected value of X is equal to mu, and expected value of N is equal to lambda divided by this quantity. And the variance of S we can obtain using the various decomposition formula here. Right. So then we get this expression here. Expected value of n is known, variance of x1 is known, and the variance of n is known, expected value of x is known. Therefore, we get this expression as the variance of s. So those are the expected value and the variance. But let us derive the distribution of s also. Right? Just out of interest. The question actually didn't ask us to derive it. It only asked us to simulate and see whether, well, actually, yeah, it does, right? Because it asks us to compare the theoretical one with the, right, derive the distribution of the random sum also. Is it normal, Vilata? They are asking whether is it normal also. Right. Okay. So let's derive the density function of S here. Right. What we know is that the density function of S for a given n, right, when capital N is equal to simple n, sum of fixed number of terms is normal with mean equal to n mu and variance equal to n square, because each xi has a normal distribution with mean mu and variance equal to square, and xi terms are iid, and therefore when you are looking at a fixed simple n number of x1 up to xn terms, then that quantity is also normally distributed with n mu and n square, mean n mu and variance n square, n sigma square. Right. So now let us derive the cumulative distribution function of S. This is the marginal, not the conditional that we are looking. So by definition, that is equal to probability S less than or equal to some value, simple S. Right. But now using the total probability law, for example, we can write down this expression by conditioning on n like this. This is directly total probability of loss. We are looking at a certain event, right? A, and then we are looking at several other events, B1, B2, B3, where B1, B2, B3, all those are mutually exclusive and exhaustive. So this is a direct application of the total probability law. So you can now substitute the expression because we know that for a given n, S has a normal distribution. So that is this part here, right? This is actually the cumulative distribution, right? Cumulative distribution is uh, going to be the cumulative normal of this normal distribution, right? So this is actually S minus n mu divided by 6. So this capital pi is actually the cumulative distribution function because we are looking at probability S less than or equal to simple. So that is this part. And then probability n is equal to simple n is that the truncated Poisson distribution that we found earlier. So so therefore, this is the expression that we get when we simplify this expression here, right? Well, first of all, this is the cumulative distribution function. In order to get the density function, we have to differentiate the cumulative distribution function with respect to S here, right? This term doesn't contain S, so you can actually take that out when you are integrating, differentiating. You can only differentiate this term because this part is not containing S. Of course, you cannot take it out because n, the summation is over n. You cannot take it out, but you can put the derivative. You can take this one out of the derivative, right? So therefore, the density function of S is given by the summation of that part, and then the derivative of this part with respect to S. When you take the derivative, you get the density function evaluated at this quantity, but then you have to multiply that by the derivative of this quantity with respect to S, right? So that's where this term comes from, right? So therefore, this is the density function of uh, the sum of random number of normal random variables, FSS, right? Now, if you look at this quantity, it's a infinite sum, and this part itself is a normal density function, right? Normal density function, right? And this can be considered as some kind of weight, depending on n. So if you look at this quantity, actually this is the truncated Poisson mass function. When you add if you add only these terms over from 1 to infinity, you know that that has to be 1, equal to 1. And I have shown that it is going to be 1 also mathematically, but even without doing this calculation, you should understand this is the mass function of the truncated Poisson. Therefore, the sum of those terms from n1 to infinity should be equal to 1. So therefore, these terms can be considered as some weights where the weights are adding to 1, right? So therefore, this thing can be considered as an infinite sum of weighted densities. This kind of term is one that we earlier in part 1 called the mixture distribution, right? Mixture distribution, right? These are some densities. Of course, these densities are not the same. They are different densities now because the density depends on n, right? So even though they are different densities, these can be considered as the proportions because they are adding up to 1, right? So some proportions times the densities adding over n from 1 to infinity, that's giving you a mixture distribution of infinite number of random variables, right? So S is not normally distributed. This is not the density function of a normal distribution, right? In general, it is an infinite mixture of normal distributions. It's an infinite mixture of several normal distributions, different normal distributions. It is not a single normal distribution, right? So the question asks whether it is normal. No, it is the sum doesn't have a normal distribution. Now, we will verify this result that we obtained by generating the CDF and also drawing the theoretical CDF that we got. Is the CDF that we got. So we can theoretically, because we know this pi function that is given by p norm function, right? So with this n, of course, we can get, but only thing is that when you are getting this, calculating this quantity in simulations, you cannot practically add an infinite number of things. So what we are going to do there is to consider only a large enough number of terms in here. So, and ignore some of the terms where these terms will be very close to zero, right? So we will ignore the terms where these terms are very close to zero. So we will first find out some n beyond which these terms will be almost zero. So therefore, we will be approximating this quantity by adding these quantities from 1 to that number only, right? So that's some approximation that we have to do, right? So the following R code simulates the random sum, compares this cumulative mean and empirical mean and variance with the theoretical values, and plots the theoretical and empirical CDFs. And also I'm uploading the histogram of the PDF also, right? So I have separated the whole program into several parts because the program is little long and I cannot put all those things in one slide. So first of all, I'm going to assume some value for the lambda. Lambda, I'm going to take, for example, lambda to be equal to 4 and mu to be equal to 10 and sigma to be equal to 3. And I'm going to consider about 10,000 simulations. Right. So I will calculate S once and I'll calculate S again. I will calculate S again and like that. 10,000 times, and then from that I can get the cumulative distribution function of S and also the density function of S simulated using the simulated data, right? So as you remember, we need to generate the data from the truncated Poisson distribution. So there is no built-in function in R for that. So I wrote down a function for that to generate random numbers, right? So what I do here is this. First of all, I consider some uniform random numbers, uh, and I'm going to consider them as some probabilities. First of all, standard uniform random numbers are between 0 and 1, right? So they can be considered as some probabilities also. If you want, right? Even though they are random numbers, they can be considered as probabilities also, random probabilities, if you will. But here, what I'm going to do is I'm going to consider uniform random numbers between uh, P naught and 1, where P naught is the probability that uh, uh, the n is equal to 0. N is equal to 0, right? So therefore, I will have uniform random numbers from that number to 1, right? Probability n is equal to 0 to 1. So I can do that by doing this thing. Let's consider u to be a uniform random number. So get some random numbers, for example, and then convert. Suppose, for example, we convert them using this transformation here, a plus b minus a times u. U are uniform random numbers. Then from this transformation, these x values will be also uniform between a and b. So this is the usual transformation you can use to transform uniform 0, 1 into some uniform a to b. Right. So I'm going to use that kind of theory to generate some uniform random numbers between something called P0 and 1, where P0 is the probability that n is equal to 0, right? In a uniform Poisson distribution, usual Poisson distribution, because I want to exclude that, right? So I calculate this P0 as the exponential minus lambda. That is actually the, if you can get it, if you want, as the d Poisson lambda also. D Poisson 0 lambda, if you want. From a usual Poisson distribution, it is either e to the power minus lambda or it is the same as d Poisson 0 lambda, right? So now I want to get some probabilities between P0, that value, and 1. Right. So therefore, I apply this transformation so that this value here will be P0, B will be equal to 1 here. So therefore, my transformation will be A is equal to P0 plus 1 minus P0 times U. Right. So therefore, I use this command here. First of all, this inside thing. Let's consider P0 plus 1 minus P0 times R unif N, where R unif N gives you N random numbers from 0 to 1. These capital U's. So this expression converts uniform 0, 1 random numbers into uniform P0, 1 values. Where P0 is the probability that the random variable is equal to 0 in a usual Poisson distribution. Right. So now if I take the quantiles corresponding to those probabilities in a Poisson lambda distribution, the random variable equal to 0 will not happen, right? Because all the probabilities are from P0 to 1, right? The probability that the random variable equal to 0 doesn't happen there, right? The event that the random variable equal to 0 doesn't happen, right? So therefore, by calculating Q points of those probabilities coming from this one with the lambda Poisson distribution, in that case, I can use the usual Poisson distribution because uh, I have removed the possibility of getting the 0 as a possible value. So Q points values give me some values. Those values will not include 0, and therefore these values can be considered as coming from a truncated Poisson distribution with 0 truncated values. So that is the first step. Write down the random the function to get random numbers from uh, truncated Poisson distribution. And then what I do is I can generate random number n using that function. I want because I'm going to consider n sim number of simulations. For each, I need the value for n. So therefore, I generate using that previous function n sim number of random numbers with the given lambda value, and then I put it in capital N. So therefore, 10,000 capital N values. In the first sum that I'm going to consider, it will consider n1 number of random variables, each normal. And in the second sum that I'm going to consider, it will consider n2 number of random variables, each random variable is normal, and so on. Right. So now simulate the random sums. Get the random sums, again 10,000 values. I use the function V apply. V apply to what? V apply to this vector. And then what function should I apply to that vector? Right. So this V apply function applies whatever the function we give here to each component of this n separately. Right. And then give us one value at the end, right? For each n, right? For each n, one value at the end. Numeric one means one value at the end, right? So what is the function that I'm going to consider? I'm going to consider it as write it as a function of simple n. Doesn't matter. You can use any letter here. as long as you are using the same letter here. So what I'm going to do is I'm going to generate normal random numbers, n number of terms, with mean with given mu was given earlier, standard deviation sigma was given earlier. So the program knows values, and take the sum of those n normal random numbers, right? So this is the function that is applied to values of this n. So therefore, when you apply this function, first of all, this n will be the first number of this capital N. Second n will be the second number of this capital N, and so on. So for each, I get a sum of a certain random number of normal random data. And so S1 will be, for example, the value that you get by taking the sum of those in one number of normal random numbers coming from normal distribution with mean mu and standard deviation sigma. And then S2 will be another number, S3 will be another number. So using this function, using this code, we can simulate the random sums. So 10,000 random sums. The function we applies the specified function separately to each element of n. Right. And then what I do is I want to get the mean of those S values and the variance of those S values and so on. So first of all, I calculate actually the theoretical mean and variance of S. We have already got the expressions. So mean of those n values has to be lambda divided by P0 value, P0, where P0 is the probability that n is equal to 0, right? So that was the normalizing constant actually, right? So that is the theoretical mean and theoretical variance. Again, I had an expression earlier, so this is that expression. I calculate using that expression, lambda over 1 minus P0 minus lambda square times P0 divided by 1 minus P0 square. So that is coming from the expression that we obtained. So these are the theoretical mean and variance of n. And then I calculate no, I'm sorry. I made a mistake. Actually, what you have is not the mean and variance of S. These are the mean and variance of N, right? So yeah, what we had already obtained mean and variance of N earlier. So these are the mean and variance of N, not the mean and variance of S. I felt like I said S. That's why I said it's a mistake. But anyway, these are the mean and variance of N, which we derived earlier. We need this one to get the variance of S theoretical values. Right. So mean and variance of the random sum, again, as we derived, it's going to be mu times the mean of n, where mean of n is the one that we got a few minutes ago here using this command. Right. And the variance of S theoretical one is equal to this one. Again, we have derived this expression. Right. So that we obtain theoretical mean and variance for the random sum S. And then we get the empirical results also, and then put them into one output, and then get the output. So in order to get the empirical ones, what we do is we calculate the mean of S and variance of S, right? So here uh, some output called results. I'm going to put them in some rows. Two means will be in a row, theoretical mean and the simulated mean, and theoretical variance and simulated variance. So first of all, first component of this result is going to be called mean. It contains theoretical value, yes, the mean of S theory that we have already calculated, and empirical value will be the mean of S. So it is calculated directly inside this command code here. So these two parts will be called theoretical and empirical. Those will be contained in vector mean. So the first component of mean is theoretical and the second one is empirical. And similarly, variance will be your vector. The first component is called theoretical, variance as theory that we just got, and then empirical value will be the variance of S directly coming from S. So this, and then when you say print results, we can get this thing and we can compare. For example, theoretical mean has to be this number, empirical value you can see very close based on 10,000 simulations of S. And the variance has to be this number. Of course, variance will be slightly far away than the mean, but still, this is the variance. If you calculate the standard deviation would have been much closer, right? These are in square terms. Okay, so that is a comparison of mean and variance. Now we will look at theoretical CDF and empirical CDF. So in order to calculate theoretical and empirical CDF, we will need some predefined values of S. We need to calculate, especially the theoretical distribution when you are calculating. We have to calculate those values at some specified values of S. So therefore, I call it X grid. And you can call it S grid. S grid would have been better name. But that is I'm considering as sequence of minimum of those S values that we already have, because we want to compare theoretical and empirical one on that range. We don't need to look at apart from those values far away, right? So minimum S and maximum S, I'm going to divide that range into 1,000 numbers. So I'll be calculating theoretical CDF using the formula that we derived. And also I can get the theoretical PDF using the formula we had. But of course, when you're calculating it, we need to consider, remember the theoretical expression had summation from, it's an infinite summation. So as I mentioned, we cannot calculate an infinite summation here. So we will decide some n so that the terms coming after that 10 will be almost zero. And therefore, when you're adding, the summation will not change that much. So, so this is the expression for the cumulative distribution function of S. Notice that here this is summation. But in order to calculate in the computer, we need to find out some value for n. So let's call it n max, right? So we are going to find n max at that. This probability here, n less than or equal to n, because we are adding here for n from n to something. So we will be considering n equal to n. So we are going to consider all those n values so that n less than or equal to simple n will be a high value. Therefore, the probability that n greater than or equal to n will be a very, very negligible amount. So therefore, I'm going to consider a certain small tail probability like 0.00001. And therefore, we would expect, we want to find out some n max so that probability n less than or equal to n max will be greater than or equal to 1 minus that very, very small probability. Right? In other words, probability n greater than that number will be that tail probability that we are going to consider as a very, 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 very small probability. So what is the value of n satisfying that condition is the question, first of all, right? So in that case, we'll be approximating this quantity after finding out n max. We will be approximating this quantity by this expression here, replacing this infinity by n max, right? So in order to find out this n max, what I did was the same thing that we did earlier, right? So consider some uniform random numbers from P0 to 1, where P0 is the probability that n is equal to 0 in a usual uniform distribution, and then calculate Q poise of those U random numbers, uniform random numbers, uh, using the usual Poisson distribution, Q poise. right? So these are considered as probabilities now. So when you're calculating Q poise for the probabilities, you get quantiles. So those quantiles will be in my n values now, right? So now I consider this expression, right? So we want n max such that n less than or equal to n max implies u less than or equal to fx n max, right? So therefore, if you consider the probability, therefore, probability of this happening this will be equal to the probability of happening this, right? Remember, what you want is to find out n max, right? Because finding n max using the distribution of n is somewhat difficult because it has truncated Poisson. So therefore, I'm going to find out n max using uniform, which is easier, right? So therefore, I'm writing this expression in terms of uniform, right? This event is equivalent to this event. Therefore, the probability of this is equal to the probability of this. Now you can find out n max using this thing because u is uniform, right? In this interval from 0, p0 to 1, right? So in that case, probability u less than or equal to some value, simple u, for example, will be given by this expression. Therefore, the probability u less than or equal to some fx n max will be equal to, you have to replace this u by fx n max, and then you will have some expression, and then from that you can get n max like this, right? So now setting this probability equal to p, right? So you want that to be equal to p, where p is 1 minus the tail probability, where tail probability is going to be a very, very small value, right? So using this expression, then I can get n max to be equal to q poise, right? Because what you have here is fx, what you need is finally f inverse of u, right? So f inverse will be given by q poise, right? Q poise of this value, right? So that will be our n max value, right? So when I did that, I found out that n max is 25 here. So all the terms after n equal to 25 will contribute only a very, very, very negligible amount to the sum, infinite sum. Therefore, it is enough to consider 25 terms in the summation. So with that, I calculate, now I get n values, uh, sequence of values n 1 to n max values, right? N values. And thereby I calculate the weights to be d poise of those n values with parameter lambda divided by 1 minus p0 for the uh, to get the truncated Poisson. Those are our weights in the mixture distribution, right? I showed you that they are actually probabilities now. So they are actually the weights of our uh, individual density functions. So we need the weights up to 25 values, right? Uh, to get the mixture CDF as well as the CDF of the mixture as well as the PDF of the mixture. Right. So theoretical CDF I obtain using the formula that we have derived, right? Sum of weights times the P norm, right? At x values, right? This is just a function. We have to apply this function to our x values. This is the function to get, right? So that is given by this expression. And then empirical ones, of course, we can get using the ECDF function applying to S. Once you apply ECDF function, it contains several components. From that, I extract the CDF evaluated at our X grid values, right? Because this one contains the CDF at each observed value of S. I don't need CDF of each observed value of S. What I need is the CDF, empirical CDF at only at the same grid values there where we calculated the theoretical CDF. Then it's easy to compare, right? So I get the empirical and then plot those two things in the same graph using this code, right? So here then I get this graph. This contains, even though it looks like one graph, it actually contains two lines, two curves. One is the theoretical CDF, the other one is the empirical CDF. So you can see that those are almost exactly the same, right? So therefore, we can see that our simulation is also correct. And here I have not drawn the theoretical density function, but here I have shown the empirical CDF. Actually, it's not the CDF, it's the frequency, but I could have calculated the density. In that case, it will have the same shape because all these bars have the same width, right? It will have the same shape. I just wanted to have look at it. So you can see that definitely that S doesn't have a normal distribution, right? So here in this case, we saw it's a mixture of infinite number of normal distributions. And by looking at the formula also, we saw that it is not normal. Now we see that it is actually a skewed distribution. It's not a normal distribution. Right. So that was a long problem, right? It had a lot of things to discuss. Now we will look at another interesting question, a little bit more complicated also. Here also we are going to look at uh, the sum of random number of random variables. Right. So here we are going to look at the number of cancer cells, uh, starting with the given number of cancer cells. What will be the number of cancer cells after a given period of time, T? Right. Cancer cells are cells with inflated or uncontrolled rate of proliferation. The uncontrolled cell division leads to rapid tumor growth. Let DIT indicate whether the ith cell divides during the time interval from t to t plus 1. Right? It is assumed that uh, DIT it takes value 1 or 0. 1 means the cell divides into 2. We are considering only dividing into 2 in a given period of time. DIT is equal to 0 means it doesn't divide, and that in that case the cell will die. We are going to assume that those cells that don't uh, are not divided, uh, then they are going to die. So we are going to assume some probability distribution for this DIT. Uh, Probability, we are going to assume probability DIT is equal to 1. So that means any cell will be divided with probability P, and therefore it will not be divided. That means it will die with probability 1 minus P. Where a dividing cell produces two daughter cells, right? So that cell becomes 2 now, and those are called daughter cells. While the cell that does not divide is assumed to die, right? So what we are interested in is actually uh, the distribution of the number of cells, these cells at t plus 1. Right? So that's what we are interested in. If yt denotes the number of cells at time t, then for each I such that dit is equal to 1, the corresponding cells divides into two daughter cells. For all I such that dit is equal to 0, the corresponding cells die. Therefore, the number of cells at time t plus 1, which is denoted as yt plus 1, will be 2 times sum of those dit terms, where the number of terms will be equal to yt, because at time t, there was yt number of cells. So for each of those cells, there is a corresponding dit, right? So whenever dit is equal to 1, the corresponding value at t plus 1 will be twice, 2 times 1. Right? When dit is equal to 0, the corresponding value will be 0, right? So therefore, yt plus 1 will be therefore twice the summation of dit is where I is going from 1 to yt, where yt is random. Right. So therefore, assuming that all cell division is independent of the current number of cells and that every cell has the same probability p of dividing, right? So therefore, each cell has the same probability of dividing and 1 minus p probability of not dividing. Then the expected value of yt plus 1 given yt is equal to the expected value of this quantity given yt. So in that case, for a given yt, this yt can be considered as a fixed value. So we will be looking at expected value of this quantity with the considering this yt as a fixed value. So in that case, expected value will be equal to 2 times yt times expected value of dit, where expected value of dit will be equal to p, where because each dit is Bernoulli with probability of success p. So therefore, expected value of yt plus 1 given yt will be equal to 2 times yt times p. Right. So therefore, expected value of yt plus 1 as the marginal one, not the conditional one, will be equal to the expected value of this quantity. That is repeated expectation, right? If we want to find out expected yt plus 1, that is equal to expected value of yt plus 1 given yt. Right? So therefore, expected value of yt plus 1 can be written as this one, where now we know this is equal to 2p yt. Now 2p is constant, but yt at this point is random because we are taking this expected value with respect to this yt. So 2p times expected value of yt. Right? So expected value of yt plus 1 can be written in terms of expected value of yt. Right. Now, let us make an assumption. If the initial number of cells at time 0 is equal to y0, suppose that is simple y0. So that is a fixed number, right? Initial number of times that we are considering at time 0 is equal to that. So if you apply this expression repeatedly, so y1, expected value of y1 will be equal to 2p y naught, because expected value of y naught will be just this observed value y naught. And then expected value of y2 will be, again, the expected value of this quantity, that will be, right, in that case, 2p square times again y naught. Right, because in that case, 2p will come. Again, expected value of y naught will be 2p y naught. So therefore, 2p will be squaring, right? And so on. So therefore, expected value of yt will be y naught times 2p to the power t, right? If you look at the general pattern here, you can write down like this. Expected value of yt is equal to y naught times 2p to the power t, where p is the probability that any cell will be divided between t to t plus 1, for example, in a given in time interval. Y naught is the initial value. Therefore, the expected number of cells increases. So, whether this number is increasing or decreasing will depend on the value of p actually, because y naught is a fixed value. If p is less than 0.5, this will be a decreasing quantity with t. If p is equal to half, then 2.5 will cancel out. This will be 1. So in that case, this will be constant y naught for all t values. If p is greater than half, then this quantity, this function will be an increasing function, right? So that's what I have mentioned here. Therefore, the expected number of cells increases when p greater than half, remains constant when p equal to half and decreases when p less than half. Notice that these statements concern the expected number of cells. The actual number of cells may differ from its expected value. So we are here getting the expected value, not the actual number, right? Expected number will be increasing or decreasing. Of course, most practically, p will be a positive a number greater than zero point 0.5, usually in a cancer situation, right? So therefore, expected number of cancer cells will be increasing. That the expected number of cells grows exponentially when p greater than zero point 0.5, remains constant when p equal to zero point 0.5, and decreases when p less than 0.5, right? Okay. So now let us look at this thing, expected value of yt, and also yt also in simulations. So I have again considered my program. I have divided the program into two parts. Let's consider, for example, y naught to be 100. Let us assume that at the beginning there were 100 cells. And let's consider a p value which is just slightly greater than zero point 0.5. Let's assume p to be 0.501. It's only a very minutely greater than zero point 0.5. And we can see what possibilities are there. So we are going to consider 365 days. So T will be 365 that I'm considering. So I will be considering 500 possibilities. So let's consider, for example, 100 cells and then allow it to uh, change according to this procedure, and then look at the situation after 365 days. So that will be one possibility. And then consider again, starting with 0 cells, consider this process, and then after 365 days, we will look at where the process is, how many yt values and so on, right? So we will do that for 500 times. And then we'll see, for example, we will just consider for this particular example, suppose a person at this point, at some point, say, for example, has not at even 365, but at some point, his actual set number of cells is greater than 1,000, that person then dies, for example. Let's assume so. So then we will look at, out of these 500 possibilities, how many possibilities will have a number of actual number of cells greater than 1,000 out of these 500 possibilities. So that will give you the probability of deaths out of this 500 as an estimate. So the time I'm going to consider from 0 to number of days, 365. And then generate these tumor parts according to this mechanism. I'm not going to explain this R function here. Actually, there is a R function in the book also. This function is not the same as the function in the book, right? So if you want, you can compare those two. I will just leave this one for a few minutes. You can copy and save, get a copy of this thing if you want. So I have written down, actually, not really me, I got it from AI and then changed some of the things according to the way that I want. So expected number of cells, we have an expression already. So there, that was, we also, that it's equal to y naught times 2 to the power time, right? So we get the expected number of cells and also the actual number of cells. And then I calculate those quantities using the simulation. And this is what I got. And you have a similar graph in the book also. Right? So here we have 500 paths, possible paths, right? At the beginning, we are considering 100 cells. So therefore, for each of those 100 cells, they are becoming large number of cells after some time, right? So this is the threshold that I'm considering, 1,000. So some of the parts, actually, in some of the parts, you can see that uh, uh, that number, the total number at the end of 364 actually becomes larger than this one. Right. So what I have here is 365. You can see that this person is, for example, uh, exceeded the threshold or even less than 200 days. So some of those people have uh, exceeded the threshold in say 200 days, 300 days. But when it comes to 365, all these have exceeded the threshold. So therefore, the probability that probability of a person dying is equal to this number of parts divided by 500 parts. Right. So that came to be, when I calculated, it's going to be approximately 6% in this simulation. Right. So if you do another simulation, it might be somewhat some other number, but still close to 6% indeed. Right. And what I have here is actually the expected number of cells, right? So you can see the expected number of cells is increasing, but of course the actual number of cells can have a large variation around that expected level, right? So as the time goes, the variability is increasing. The mean is also increasing, but the mean is not that increasing that large, that in a very huge range, but the variance is increasing. Right. So that is what we can see from this simulation. Right. So that is also the end of this lecture. So that is the end of the second part of this lecture. Right. So in the next lecture, we will discuss about regression and correlation again, because in the regression also we are having mixture of distributions, right? So the response variable, the distribution of the response variable is changing with the value of x, for example, if you're considering a single x, right? So if you consider the distribution of all the y values, it can be considered as a mixture of normals, right? So we will consider that situation and then general regression problems in the next lecture.